We want to solve this. Our variable is y instead of x, but that doesn't really matter at the end of the day. And I'm sorry, this is supposed to be negative 20. Negative 20. And I don't know what happened. I had a complete brain fart. This is minus 10y. I looked at one thing and I wrote down another. So we want to solve this. This is clearly a quadratic because as you can see, we have a squared variable in there. We have a variable to the regular first power. We have a constant. One thing we like whenever we solve quadratics, unless we're going to use completing the square, we like everything to be on the same side of the quadratic. And so what I'm going to do is I'm going to add 20 to both sides so that it's set equal to 0. That's what I want. Y squared minus 10y plus 20 equals 0. Now, the next thing I would probably want to at least try to do, I would probably want to try factoring that. Factoring is really popular. There's a lot of reasons it's popular. It's because it's generally pretty much the most straightforward or quickest way to solve these. But that doesn't mean it's always going to work. It may not factor the way you quite want. So we have a 1 in front of the y squared. So 1 times positive 20 is positive 20. We want two numbers which multiply to positive 20 but add to negative 10. And you can, try really hard. You can strain your brain a little bit. You're not going to find two integers that do that, two nice whole numbers, whether positive or negative. That's just not going to happen. -4 and -5 comes close, but those add to -9, not -10. So it turns out you can't really factor this, at least the way you want, which is to have integers. Theoretically, it can be factored, but it's an ugly factoring that we don't really want to talk about. So now we have to look at other methods for solving quadratics. We can try completing the square, but since I already moved the 20 over, let's just use the quadratic formula. So this quadratic formula is written on the brain of every math person till the day they die. The quadratic formula is going to be -b plus or minus the square root of b squared minus 4ac, not AC Slater, all over twice a where a is the coefficient of your squared term, which since there isn't a coefficient written, it's an implied 1. B is the coefficient of your first degree term. C is the constant, as long as everything's written in order on one side of the equation. And so this is going to be our solution. This is how we do it. The plus or minus automatically implies that we go down two paths, and that's what adjusts for the possibility of having two different solutions here, which you're usually going to have that case, unless this thing, remember called the discriminant, happens to go to 0, which it usually doesn't, but sometimes does. So let's plug things into this. Let's use orange. So it'll be -b. So b was already -10. So -b will be +10. It's just the opposite side. Plus or minus the square root of b squared -10 squared minus 4 times a is 1 times c is 20. all over 2 times 1. So the important thing is to keep track of signs here. What's positive, what's negative, what's happening. So we're going to have 10 plus or minus the square root. Negative 10 squared is 100. Minus 4 times 1 times 20 is 80. All over 2 times 1 is 2. Now there's going to be a bunch of ways that we can simplify this. Let's try simplifying what's in the square root first. 100 minus 80 is 20. Now, what we can say, there's a couple things you can do. What we want to do, this is technically a correct answer here, although I'd want to go and do the plus and then the minus path. But what we want to do is we would like to simplify as much as we can. And it turns out there's a whole heck of a lot more we can do with this one. You'll notice that this 20 inside the square root, if you remember simplifying square roots, what you can say is that 20 is really 4 times 5. And then what you can do is you can bring the 4 out of the square root by taking its square root, which will give it a 2. The reason you don't take the 5 out is because 5 doesn't have a cute little nice clear square root. So you could rewrite this as 10 plus or minus 2 square roots of 5 over 2. And now here's where something slick happens. This 10 is being divided by 2 essentially, as well as this 2 square roots of 5. So a little cancellation is going to occur. 10 divided by 2 is 5. These 2's can cancel all the same. So what we're going to end up with, let me just answer this. Send it to me in chat and I'll work it. So what we're going to have is 5 plus or minus the square root of 5. These 2's are gone. There's just a 1 on bottom, which is to say there's nothing to worry about on bottom. So we just say 5 square roots of 5. So then finally our solutions are going to be 5 minus the square root of 5, which is going to be some nasty number. There's no sense crying over spilt milk on that one. And then 5 plus the square root of 5. Okay, so that's number 2 on the review, if you're curious. Gracie asks a good question on number 34. What it wants is it wants something called the cofactor of matrices. So we can work that one out together. Now, one minor thing, technically we used cofactors, but we didn't go into uber detail about all of the different terminology because I didn't feel it was necessary. So we're going to work a problem on the review. Number 34, I'm going to give you a matrix, and we're going to be taking its determinant. So it's going to be -2, 6, 3, 1, 4, 1, -3, 1, 4. And then what we're going to do is I will show you what in the heck it even is asking for. It wants you to find the cofactor of each element on the second row. So technically we didn't define what a cofactor was, but here's the skinny. It's actually just going to be part of the entire process that you've worked already, that you've already worked yourself whenever taking the determinant of a 3x3 matrix. So I wouldn't worry too horribly much about this particular type of problem showing up on the final exam, because it won't. What it'll do is it'll just say, here's a 3x3 system, solve it using Cramer's rule. And so you'll just kind of know, well, I just need to take the determinant of this. So I can still work this problem. What it's going to want us to do is it wants us to expand along the second row. Now, if we were to expand along the first column, the formula works one way. And if you remember, I showed you how to do it expanding along the first column. And that was kind of where we sat with it. I didn't want to overwhelm the senses at the time, but technically if you expand along a different row or column, it might look a slight bit different, just depending on, how you're choosing to work it. So what we're going to see here we would start with, say, this thing. And remember, we would delete the row and the column that it was found on. And we would multiply by the determinant of the leftover matrix, which would be 6, 4, I don't know, I'm sorry, 3, 1, and 4. Now, what I left out for simplicity's sake is that technically you multiply by -1. So this is, and you'll see why I left this out. Raised to the power of the sum of the row and column that this was on. That's why I left it out, because it's silly. This entry here, this original 1, is on the second row, so 2, first column, so 2 plus 1. In other words, it's -1 to the third power. Excuse me. And now this thing altogether is called the cofactor for that first entry of 1. It's this part is the cofactor, and then this is the entry itself, 1, that you're multiplying by. So you can kind of see why I left all that terminology out, It's because it's unnecessary. If you expand along the first column, which is usually the best way to do it in most cases, you're not going to have to worry. And I was able to kind of sidestep a really nasty formula. So yes, there is this question on the review. On your final exam, it's not going to be asking for cofactors. It doesn't get that granular with it. It just might want you to calculate a 3x3 determinant. And I felt you just didn't have to know all this little individual terminology here. But if you're curious, this cofactor, -1 to the third is -1. Then we can take the determinant here. It'll be 6 times 4 minus 3 times 1. It'll essentially come out to -21. Again, though, it's not something that we should focus on too horribly much, because you could have just expanded along the first column here, and we've already handled this -1 to the whatever power thing. We handled that a separate way. But at any rate, that's how you can find cofactors of matrices. So good question. Let's see. Let me take a look at a different one. This is going to be number 32. So this will be from chapter 4. And it wants us to express the solution in exact form. And it's going to be a logarithmic equation. ln of 4x minus 5 plus ln of x minus 5 equals the natural log of 25. So we are back on the topic of logarithms from chapter 4. Now, what we want to do is we want to, it says express the solution. Well, what's the solution? Well, we have to solve the darn thing in order to express any kinds of solutions in any manner. So, and let me maximize my room on here. There we go. More space there. So what we want to do is we see there's x here, there's x here. We would like to actually solve this thing. We would actually like to, figure out the value of x that's going to produce a solution here, or values of x. So there's a couple strategies we can use. One of them is we have a natural log, a natural log, a natural log. Well, a natural log, remember, is a logarithm with a base of e, where e is that very, very, very special constant in mathematics. Since these two logarithms have the same base, and then we're adding outside of the logarithms, we can condense them into the same logarithmic house. Little arrow. I can bring the 4x minus 5, and I can put them into the same house. But here's a little warning for you. You're going to want to put parentheses around these so that you're multiplying the entire 4x minus 5 times the entire x minus 5. And then you're still just equal to the ln of 25. So we've done a good first step here. Our next step, notice The entire left side is inside of a logarithm, as is the entire right side. These logarithms have the same base, so we can just equate their arguments. In other words, the only way that this entire left-hand side is going to be equal to this entire right-hand side is if the business inside the ln is equal on both sides. That way you're taking the natural log of the same thing on the left as you are on the right. So we can kind of drop things a little bit. We can basically drop the natural logs. They're not actually gone though. So one thing to note, when we drop the logarithms like this, we have to check our solutions in the final answer. We have to make sure that our solutions are not going to create problems in the original problem. And that's because what we're doing by dropping the natural logs is kind of not a very precise mathematical operation. It's not one that's completely foolproof. So the way we make it foolproof is that we need to check our solutions. But the good news is now there's no logarithms in this, and we can just solve for x. You're going to need to FOIL this side out. And what you're going to see is you're just going to end up with a quadratic. So remember how to FOIL. It goes like that. And we're going to end up with 4x squared minus 4x times 5, 20x, minus 5x plus 25 equals 25. Just writing out what I got here. Well, we'll combine like terms. You're going to have 4x squared minus 25x plus 25 equals 25. And then we're going to have to delete some rows here. Because I'm out of space, I'll leave the original logarithm problem up there. I'll have to use some trickery. What I can see is normally when I'm solving a quadratic, I can clearly tell this is a quadratic. I want to get everything on the same left-hand side. So I got to move this 25 over, which is going to have a very wonderful consequence. Because I'm going to end up with 4x squared minus 25x. The 25s are gone. That was just a nice coincidence. That almost never happens. But every once in a while, the great king of math smiles down upon us from his golden throne, and we get some nice things like that. The reason this is so nice now is because we got to solve this quadratic. We could be boring and use the quadratic formula, but sometimes there's no need for that. What I can do, I can factor an x out of this. I'm left with 4x minus 25 equals 0. And now I just need to use principle of zero products. I set this x equal to 0. This is one potential solution. I set the 4x minus 25 equal to 0. I add the 25 over, divide by 4. I'm going to end up with that. But I'm not done. I'm going to put the box around this, around each of these. I'm going to call this a potential solution. So these are both called potential solutions. But remember this little note I made. Whenever I just dropped the natural log on both sides, I may have been using something that is a little bit less than precise, less than good. And what I mean by that is that I need to check these in the final answer. So we're going to take these potential solutions. We're going to check that they actually work in both cases. We got to check both of them. In the original problem with the logarithm. So I'm going to try x equals 0. I'm just going to straight up chuck it into the logarithm. I'm going to have the ln of 4 times 0 minus 5 plus the ln of 0 minus 5 equals, and now I'm going to have to get rid of these notes here, the ln of 25. I've reached a problem. When I plug a 0 in for x, I'm going to end up with some negative arguments inside my logarithms. Uh-oh, no. Problem, you can't have negative values inside the logarithms. If you go back to chapter 4, when we first defined logarithms, we said, no, the argument of a logarithm has to be positive. Thus, we can actually rule this solution out altogether. That solution is not going to be allowed. So x equals 0 is not allowed, so one solution's been ruled out. Let's try out this guy for size. We would want to plug x equals 25 over 4 into the logarithms. You'll have no problems this time. And maybe you can see it, 4 times 25 over 4. That'll just be the ln of 20. This is what that'll reduce to. 25 over 4 here minus 5. That'll still stay positive inside. So you'll actually be okay if you plug 25 over 4 in. I'll let you verify that on your own. So that's going to end up being our only solution. So it's important to check your solutions. So if I remember correctly, the chapter 4 exam, which covered logarithms, the last exam we took, grades were generally pretty good on that one. I think a lot of you breathed a sigh of relief, perhaps, when you submitted that exam. So very good on that. Hopefully you'll do well then on the parts of the final exam that cover chapter 4. Okay, so that was that number. I want to save that as a PDF. Let's see. The next problem we'll try working out, maybe number 28. Let me pull that. And this is straight up from your final exam review, no trickery. Another question from chapter 4. And what we want to do is we want to solve the equation. And it looks like a fun one. It's going to be 1/3 to the 5x plus 2 power equals 9 to the x minus 1 power. So this is an exponential equation. As you can see, the big kicker here, the big, not really issue, but something that may cause us a little bit of grief, is that our variable x, which is what we're trying to solve for, our variable, unfortunately, is tied up at the moment. Our variable is in the exponent. It's in the exponent, which is something we don't normally like. I can't just, guess and check, try different values of it and hope that it works. So what we're going to have to do is we're going to have to find some way, some strategy of making our variable no longer in the exponent. That's our goal here. So there's a couple ways you can do this. Just as a little side note, this is a problem from section 4.2. You could solve this one using new knowledge gained from future sections involving logarithms. That is, you can use logarithms to solve this problem, but we actually encountered this kind of problem before we encountered logarithms, meaning there's a way to solve it without using logarithms. And so I'm going to focus on that way because it's kind of a little bit more slick. It's kind of neat. It's kind of neat. So we're going to solve it without logarithms. How do I do that? Well, I'm going to give you a hint. If this had been 1/4 here, which it's not, we'll go back to 1/3. If this had been 1/4 here, the little slick trick I'm about to use will not work. It won't work because this 1/4 can't be expressed as a power of something that this could be expressed as, and the bases line up. What in the world do I mean by that? Well, actually, just undo. There you go. What I mean is that 1/3 can actually be written as 3 to some power. 9 can also be written as 3 to some power. So rewrite both sides as 3 raised to some power. Again, if this had been 1/4, I don't have such a cute little option. Well, first of all, 1/3 here is really 1/3 to the first. We can actually use negative exponents here. And I can rewrite 1/3 as 3 to the negative first. And then there's still a 5x plus 2 power. That's going to be what does it for me. Now 9, I can rewrite 9 like this. It's the same thing. 9 can be written as 3 squared, and then there's still an x to the an x minus 1 power over there. And now once I take care of rewriting the exponent, I'm going to end up with 3 raised to some power equals 3 raised to some power. And that's going to be awesome for us. The way I need to deal with those exponents, I'm going to need to distribute this -1 here, because one of our exponential laws says if I'm raising a number to a power twice, I can multiply these powers together. And when I say multiply, I mean the entire thing. Same for this too. So now what I'm going to do is I'm going to bring all this down a little bit, just so I have some more space. And I'm going to come over here, go. And that's just the limitations of this whiteboard we're dealing with. So when I distribute this -1 power, I'm going to have 3 raised to the -5x minus 2 power. Then I distribute the 2 on the right-hand side, 3 to the 2x minus 2 power. Why in the world did I do that? Because now both sides are just 3 raised to some power. So I can just equate their powers. Because think about it, whatever x value you plug in here, whatever the solution is, it needs to be so that this exponent and this exponent are the same, so that it's just 3 being raised to a power equals 3 being raised to that exact same power. So this was the cute little trick we did in chapter 4. That's why I endeavored to rewrite all this as a base of 3 problem. So I can just equate their powers now. Negative 5x minus 2 equals 2x minus 2. Why I put 4. And now, let me see. Let me look at something closely here. Did I make a mistake somewhere? No, I don't believe I did, but I'm not getting. It's always easy to make an arithmetic mistake whenever you're working problems. Nope. Okay, so next up, we just got to solve this thing. Oh, no, I didn't make a mistake. What am I saying? Nope, we're good. We can move the x's to the left-hand side. This is just a simple linear equation now. You can have negative 7x minus 2 equals negative 2. You're going to add 2 to both sides to get the x by itself. You're going to end up with negative 7x equals 0. Now, technically, you have to divide both sides by negative 7, but you can tell it's just going to give you x equals 0 as your final answer here. Now, technically, we should check the solution. We should check x equals 0. We should plug it into the original equation. We'll just do it verbally. It's going to be okay. 1/3, you put a 0 in, that's going to be 5 times 0 plus 2. That's going to be 1/3 to the second power, which becomes 1/3 squared, becomes 1/9. You put a 0 here into the right-hand side. You're going to have 0 minus 1. You're going to have 9 to the negative first power, which shoots the 9 to the bottom and becomes 1/9. In other words, this does work. So the solution works. And you'll remember, I thought I had made a mistake in there, and it turns out I hadn't. So sometimes it's easy to overthink some of these problems. But that's just kind of the burden of mathematics. It's very easy to think you're wrong when you're actually right. That's where you need confidence. What's really funny, and I know you guys aren't going to believe me when I tell you this, but a real life tip here, I call it blind confidence. As long as you've put in the time, you've put in the studying, you're not just trying to pull a miracle out of nowhere. If you put in the time and the studying, but you get nervous during or before an exam or something, you're so worried about it. I actually have a couple of tips for you. I have a couple of tips for you that I promise you work. If you have really truly done the studying, you actually know a lot more of the math than you believe you know. So, but you go into the exam, and because you don't believe that you know it, you make mistakes that are silly because your mind is not connecting the proper dots, even though the knowledge is there in your brain. I would imagine that happens to a lot of us. That certainly happened to me when I was in school. It happened all the time. There's a couple solutions to that. One, you could take an attitude that, well, at the end of the day, none of this really matters. And I don't mean in a life sense. I just mean, hey, I don't do quite as well as I had hoped. It's not like my entire future is completely derailed off of that. And that's very true. I believe that very much so. That doesn't mean don't try, but it does mean that, it's not like the die is cast on what you're going to be in 10 years based on how well you did when you were 16 or 17 or 18 in high school. I promise you that is not how the world works, not for 1 second. So definitely take this stuff seriously, but you need to tell yourself, look, I'm not going to die if I don't do quite as well as I thought. It's not going to be the end of the world. Wormwood is not going to crash into the Pacific Ocean and cause another ice age or something. It's not the end of the world. Ironically, by having that attitude, even though it sounds like you're not taking it seriously, by having that kind of an attitude, you actually unlock the knowledge you have in your brain because you no longer are so nervous about the exam. And then you end up doing better on it. And like I said, you guys aren't going to believe me. You don't believe me, maybe. You're like, no, what is Josh talking about? But I promise you, it works. It works to just kind of have that kind of an attitude. Another attitude you could take is what I call blind confidence or stupid confidence, where as long as you know what you're doing, just tell yourself that you understand it and that you're confident. It's like a sales trick. In sales, you just say, look, I'm going to walk up to this person who's looking at this car or they want to buy all this stuff. I'm going to walk up to them. I'm going to make this sale. I'm going to close this deal. I'm going to get the commission and I'm going to go buy myself a PS5 or something like that. You need to have blind confidence, even if it doesn't end up going the way you want. I promise you, just by having stupid, silly, dumb confidence where you just tell yourself that you're confident, it somehow surprisingly magically works. And that is two strategies I can give you for kind of dealing with exam anxiety. Again, though, those strategies don't work if you haven't studied and you don't actually have the knowledge. But they do work if you are really good and have been doing well, and then you walk into the exam. So just some tips for you gathered from my years of, I've been in school years and years. I've done years of college myself. Number 29. Number 29 is going to be a graphing problem. We're going to work it together. I'm just going to show you the graph itself. I'm going to make this larger. Let me use my magic here. So let's look at it. So we're going to want to graph the exponential function using transformations where appropriate. So the function is 2 raised to the x minus 3 power. Now we've got the basic shape down. You remember the basic shape of an exponential function. If your base is greater than 1, which it is here, our base is 2, it takes this upward sloping kind of hockey stick look. So it goes up like this. What it's going to do, there's a few key things. For one, we can zoom in on this to see it a little bit better. We can even, I believe, we can open it up and look at it more closely. The question is, which one is it? Well, what we do is we take the base exponential, and because it's minus 3 to the x, what that's going to do is it's not going to shift it to the left 3 units. It's actually going to shift it to the right 3 units. And so it looks like this one's going to be the winner here. It's shifting everything to the right 3 units. If you look at some of these other ones, it looks like this is the parent function. It looks like this one was shifted to the left, and it looks like this one was shifted down 3 units. No, it's telling me that that was the correct one. But that's the reason behind it. So we need to remember, if you remember all the way back in chapter 2, we reviewed the transformations of functions, and now we're just taking it to the next step, and we are applying that to an exponential. But transformations of functions, that's going to ring true no matter what kind of problem you're working, what kind of a function you're dealing with. So a good one. What I'll do now, those are all the ones I've been requested to work on the review. I'll give you guys, how about 30 seconds? Go and see if you can find another problem, if you remember one, maybe. Otherwise, I'm just going to kind of poke around at the review, maybe try to find. Here, I'll work this one, number 9. This is a good one to refresh ourselves on. So number 9 on the review. But you guys are free to poke around the review if you're on your Chromebook or whatever in class, and you can pick a problem. We want to find the slope of the line that passes through the points. The points are 7, -3, and the second point is -8, 2. So this is just kind of a rote application of the slope formula. If you remember the formula for finding the slope between 2 points on a line, it's going to be m equals, it's kind of famous, y2 minus y1 over x2 minus x1. And what we do is we label the first point x1, y1. The x coordinate is x1 rather. The y coordinate is y1. We'll label this x2, y2, the x coordinate x2. And there. And then it's just simply plugging this into the formula and then perhaps simplifying the fraction that results from that. What I will say is there's a couple easy mistakes. And when I say easy, I mean it's easy to make these mistakes, but they're still wrong. One mistake, if I can actually grab this thing. There we go. One mistake is to accidentally get your wires crossed. And even if you don't write it down like this, I've seen this mistake all the time. No, that's bad. Don't do that. You want your x1 and y1 to come from the same point. So don't make that kind of mistake. Don't get your wires crossed or anything weird like that. You might think it doesn't happen, but you might label them correctly as x1, y1, x2, y2, but then when you plug them into the formula, you might accidentally put the -3 here first, which is not what you want. So you'll lose consistency. Now, before you just look at this one and plug it into the formula, one strategy is to pump the brakes a little bit. And what I mean by that is don't just rush into it and think you already know how to do it. I can't tell you how easy it is to make that mistake. My girlfriend is taking a calculus class at a different college. She's taking calculus. And when I sit down and I help her out with the math, I noticed she understands the concepts just fine, but she makes a lot of mistakes here and there. And I love her, and I won't tell her that I told the class this, but she'll make a lot of mistakes. And I'm like, babe, all you did was put a negative sign in the wrong place or something. And she's like, why do I always make these mistakes? And I'm like, I look at your work and you're rushing it. She'll try to do 3 steps all on one line when she's working on, doing these calculus problems. And I'm like, I trained myself to do it one step at a time, even if it slows your process down when you're learning it and when you're first practicing with a concept. You need to slow yourself down. What I mean is, if you have this kind of problem, take these points and label them x1, y1. Take the second point, label it x2, y2. Don't skip that. Write out the slope formula. Write it out. Don't just automatically plug it in and assume you know it. Write it out. Y2 minus y1 equals x2 minus x1. And so now we're going to plug the right thing in. Y2 is 2 minus, now y1 is negative 3. Here's a mistake I see all the time. That's a mistake I see all the time. No, you are subtracting here. If you are subtracting a negative number, then so be it. Subtract the negative number. Oops, oh. Subtract the negative number. It's so easy to think, oh, since the negative 3 was already negative, then this negative sign just magically goes away. No, you're subtracting a negative. That, I promise you, is a mistake that happens a lot. Then on bottom, x2 is negative 8 minus x1 is 7. So this actually becomes 2 plus 3. Negative 8 minus 7 is going to stay negative, and it's clearly going to be negative 15. So we get 5 over negative 15, which reduces to the fraction negative 1/3. And so negative 1/3 is going to be the slope of our line. Real quick, remember the rise over run interpretation of slope. The top value gives you your rise, or sometimes it's your fall based on whether the slope is positive or negative. The top value tells you your vertical change for every units of your horizontal change. So a slope of negative 1/3, a slope of negative 1/3, it falls because the slope is negative. It falls 1 unit for every run of 3 units. That is every 3 units to the right. That you go. If this had been a positive slope, it really would rise. So that means it's going to be a slope that falls. So it's negative. And it works a little something like this. It falls 1 unit every 3 units you go to the right. That's a bad 3. Let me try it again. Okay, so that was number 9. Let me go find another problem. That was from chapter 2. We studied linear equations, things like that in detail. Let's see, and just keep in mind the review doesn't cover every possible problem you could see. Technically, any concept we covered in class, you might be tested over. So if you want to get a wider range of the different types of problems you could see, remember to use that little trick where you review homeworks that you've already submitted, and you can rework the problems in there for practice. That's going to give you a wider range. The review is just kind of a snapshot. No, the final exam is not just the review with different numbers. That's not how college works. That's not how high school works. That's not how something with a lot of rigor to it works, because that's just easy. That's just memorize all the problems and then just change numbers. That's not how knowledge works. It might be easier, so you might favor it, but you know, that isn't necessarily good for you. We can do one maybe using synthetic division. Okay, yeah, let's do one synthetic division. So this will be number 18. So I think we're getting a good wide range here of different problems. Is the given number k a zero of the polynomial? I'm going to give you the polynomial and the number here in a second. Use synthetic division. Just one more space here. And our k value is going to be 3. Our polynomial is going to be x to the 4th minus 6x squared. Minus 135. Okay, so for using synthetic division, remember, what we're trying to do is we're trying to think, hey, is the number 3 a zero of this? Meaning if I plug a 3 into this polynomial, will it produce a 0? Now the easy way to do it would just to be plug 3 into this and, you know, figure out what comes out of it. But we want to do it using synthetic division. So remember, if you had a 0 of 3, the factor would look like x minus 3. It has the opposite sign. But whenever you do the synthetic division, you use the sign on the value itself. It's a little confusing, but you're actually going to use a 3 here. Now, here's the problem. If I put these in like this, if I try doing that, that's going to be a mistake. You're going to have made a huge mistake simply because this is x to the 4th. You've skipped over a potential x to the 3rd here, x squared. Then you've skipped over a potential x value here. The way synthetic division reads these coefficients here is 1x squared minus 6x minus 135, which is not what we have. So that's a very easy mistake to make. The way we remedy that, we need to think of this as, well, if we've skipped over any values, we need to represent them with a 0 coefficient. That is the proper way to set up our synthetic division. Thus, we need zeros in place there. We need a big fat stinking 0 here. And we need a big fat stinking 0 right here. And now we can do the synthetic division. We start by bringing down our first value here. We don't do anything to it. And then, and I think you guys remember synthetic division, it's nice and slick. We do 3 times 1, which will give us 3. Then we add these together. 0 plus 3 is 3. Now I do this 3 times this 3 down here, which will give us 9. Then I do -6 plus 9, which ironically will give us positive 3 again, just a coincidence. I do 3 times 3, I'll get 9 again. I do 0 plus 9, I'll get 9 again. Then I do 3 times 9, and I'm going to get positive 27. Now here's the rub. We're going to do negative 135 plus 27, but I can tell that's not going to be 0. It would have to be negative 135 plus 135. So I already know that's not going to give me 0, so I can already tell you that k is not a 0 of this polynomial. You can do the addition, you'll get negative 108, it looks like. This would be like my remainder upon division. In fact, that's exactly what it is. So this is my remainder upon division. If the remainder was 0, then k equals 3 would be a 0/root of the polynomial. However, that's not the case. So my conclusion, k equals 3 is not a 0/root of the polynomial. What does that mean? That means we couldn't factor x minus 3 out of this polynomial and slowly start to factor it and make our lives easier. So we'd like to have that as a root, but very rarely do we actually get it. Now, let's say you're working this type of problem on the final exam. Now, remember, you are required to submit your scratch work to the final. Also, I'm going to ask that you submit your scratch work ASAP. Even if there's time left when you're done with the exam, just take the pictures real quick and upload it. You guys have been really good about that, so I'm not saying you haven't been. I'm just saying I'll request that you get your scratch work in as soon as possible, because if you guys get your scratch work in, I mean, my goal is to turn around and have the entire course graded by the end of the day Tuesday. That's my goal, and that's also good for you because you'll know what you made quicker, and it won't be, as much of an air of mystery, and that's always annoying. So the quicker you get your scratch work in, the quicker I can turn around and have your grades uploaded, and we can rock and roll, and there won't be any question marks around it. So definitely, if everyone gets their scratch work in, I'm hoping to have it all in by noon on Tuesday, if you can do that. I know you might have class and stuff, but if you can get that in quickly, if you can take a moment and pause and submit that, that will be good for everybody. So that would be my request for you. Any other tips and tricks about the final? If there are any problems, I have looked at the final, I've reviewed it. I'll let you know Tuesday morning if there's any problems that we just didn't have time to cover the material in the course. I will tell you which problems those are, and I'll tell you to don't even work them till you've worked the rest of the exam, and then you can attempt those problems, but you're not going to be held accountable for them. So you can attempt them just to try them out. They won't be bonus per se, but your grade won't be, your grade will not be affected by those problems. And I'll let you know what they are before the exam, so you know what to look for. And that's just because there's so much material, and there's some things I think are just not necessary to cover. I think we got a good, nice overview of the course. So if you guys have any questions for me, I'll field questions.